Welcome to Algebra 1, Unit 5, Lesson 5-2, Relations and Functions. I'm Mr. Pilarski, and we're going to have objectives today of I will be able to identify relations and functions, and I will be able to evaluate functions. Pretty good stuff today. We're going to look at some mappings, and we're going to look at ways to determine really if a relation is a function. A relation is a pretty basic thing. We're going to see that definition up and coming here. A relation is a set of ordered pairs. Now, just to review, a set of ordered pairs would be something like this here, 2, 5, 3, 4, 0, 0, and 2, 3. This is a set of ordered pairs. Remember, this is a set of xy values that we can plot on an xy plane. We can make a graph out of this relation and this set of ordered pairs. But that's a relation right there. Now, a function is a relation that assigns exactly one output or range value for each input or domain value. This is the real important part of this sentence here. This exactly one, that implies that each x value or each y value is paired with one x value, or vice versa. That each x value is assigned to exactly one, or one and only one, range value. Another word for output or range would be the y values. And for the input or the domain would be the x values. So in our relation up here, we see we have x values of 2, 3, 4, or 2, 3, 0, and 2. Then we have y values of 5, 4, 0, and 3. Since 2 is repeated in this relation, this particular relation is not a function by definition. So we could change that relation a little bit. We can keep the first 3 ordered pairs. We don't have to keep those 3 ordered pairs, but we can. All we have to do is change the last one a little bit. And I'm going to change it from a 2 to a -1, 3. Now that we have different x values here, 2, 3, 0, and 1, for each y value, 5, 4, 0, and 3, we have a function. I'm going to give you a visual way using a mapping to do this in this first example. Using a mapping diagram. We're going to use a mapping diagram to determine whether each relation is a function. We're using a mapping diagram to determine whether each relation is a function. So we need to use a mapping diagram here. Now, to make a mapping diagram, we're going to need to list out the domain and the range. Now, the domain and the range are the x and the y values respectively. This is our y values, meaning the range is our y values, and our domain are our x values, or our input and our output. To talk about something I talk about in class, domain is the independent variable, whereas range is the dependent variable. So to do this, it's best if you list the domain first. Just listing the numbers out, 4, 2, -3, and 2. Now notice we have 2 repeating itself. We only need to put it once, and we're going to put them in order from least to great. So -3, 2, and 4. We'll repeat that process, but for our range values in this case, 3, -1, -3, and 4. And we'll put those in order from least to great. And that should be a -3 right there. -3, -1, 3, and 4. Now we'll list them over here. I always like to list the x first, or the domain values. In this case, we have -3, 2, and 4. Over here we have a range We already have those listed out. -3, -1, 3, and 4. Now, here comes the mapping part. -3 was originally paired with -3, so we draw an arrow connecting them. 2, since it was used twice, was paired with 2 different y values. This is what makes it not a function. Since this domain value of 2, for a lack of better terms, has 2 arrows leaving it, that's what makes it not a function. And that arrow should be going down here. Clean that up, put that arrow in there. I made a mistake. Mapping it to the 3. The 2 should be paired with -1 and 4. And 4 is paired with 3. This is what makes problem A not a function. And that's because two is paired with -1 and 4. That's all part A right there. That's all part A. Now, you don't necessarily have to do this over here, the domain and the range, but what I do suggest you do is at least make your mapping. I think listing out the domain first is going to help you, or the domain and the range first is going to help you make your mapping to determine whether it's not a function, whether it is a function or not. If you want to write that down, I suggest you pause the video at this time because I'm going to erase it and continue with my work. I'm going to do part B at this point. I'm going to slide part A out of the way. If you go ahead and start doing part B on your own, you may want to pause the video, see if you get it right, but I'm going to move part B up. And so I can start listing out my domain and range. The domain in this case is -4, 2, -1, and 1, and of course I want to put those in ascending order from small to big. -4, -1, 1, and 2. We can see this problem's different than part A because we have 4 domain values. None of the domain values repeated. Next we'll list out the range. And the range in this case is 0, 12, -3, and 5. And hopefully at this point you can see that we're going to have 5 different range values starting with -1, then 0, then 1, then 2. Oh, I got that backwards. It should be -1, 0, 5, and 12. Got my eyes crossed there for a minute. There we go, there's the range. So now we can make our mapping. And this mapping is going to show what's called a one-to-one correspondence, where we have our domain first, then the range. And again, you can do this right away if you want to, if you think you can put the numbers in order from the ordered pairs. -4, -1, 1, and 2 in our domain. And in our range we have -1, 0, 5, and 12. Now we're going to have some of the lines crisscrossing, but that's okay. -4 was originally paired with 0. 2 was originally paired with 12. Actually, there we go. Made a little mistake. -1 was paired with -3. This should be a -3, not a -1. Get my eyes crossed today. So -1 was paired with a -3, and 1 is paired with 5. So we can see that one-to-one correspondence. So all we really need to write here is that this is a function. I'll move on to our next example here. Actually, we have a definition or a discussion of the vertical line test. Besides creating a mapping as we did in example 1, the vertical line test can be used to determine if a relation is a function. And that should be, say, is a function, not and a function. is a function. To use the vertical line test, you need to be given a graph, or you would need to create your own. So if you're not given a graph, you can and should create your own, especially if you're asked to use the vertical line test. Here, using the vertical line test, use the vertical line test to determine whether the relation 3, 2, 5, negative 1, 5, negative 5, 3, negative 2, 2 is a function. So you can see I don't have any graph papers. A lot of students would say, oh, I didn't have any graph paper, so I couldn't do it. Well, you're going to see me do the best I can on here with my wireless slate. Draw an X and a Y axis. I don't have any graph paper. And so I'm going to graph, and we're just going to count off 1 and 2, 3, 4, 5. And what I try to do is I try to space it so 1 is about halfway, so that'd be 1, 2, 3, 4, 5. And that'll give me a gauge of where I'm going to be at. 3, 2, so that'd be to the right of the origin 3, and then up 2. So that would be right there. You could call that point A if you want to. 5, negative 1, so that's from the origin to the right 5 and down 1, which would be halfway down, so that'd be point B. Negative 5, 3, that'd be to the left 5, which would be right about there. And up 3, which would be right about there. So that'd be to the left 3 and up, or to the left 5 and up 3. That'd be our point C. And our last point, point D, is negative 2, 2. So that'd be to the left 2 and up 2. Now, if you're not sure what the vertical line test is, let's go back for a second. To use vertical line test, you need to be given a graph, or you need to make your own graph. So what we're going to do is use a vertical line, a line that goes up and down, to create or to determine if this is a function. And what this vertical line does is implies a one-to-one correspondence, that each x value is paired with only one y value. So if we see here this point, well, there's only one point on our vertical line. There's only one point on our vertical line there. There's only one point on our vertical line there. And there's only one point on our vertical line there. A lot of times if you're doing this in class, you can just use your pencil as a vertical line. So you'd write a little answer here saying that this passes the vertical line test. And is a function. Function notation. Another way to write a function or an equation, y is equal to 2x plus 5, is f of x is equal to 2x plus 5. When you use f of x instead of y, that is called function notation. That's it, something you're pretty used to seeing, y is equal to 2x plus 5. Well, instead of calling it y, we're now calling it f of x. In this example, we're making a table to form a function rule. Well, we're given here, make a table for f of t is equal to 0.5x plus 1. Use 1, 2, 3, and 4 as domain values. So we're going to take a look at doing that here. Here I have a table, and sometimes you're going to need to create this table on your own. But this one, I chose t because this is our independent variable. In this case, whatever's inside the parentheses comes here. This is our independent variable. This is our domain. Okay, this is our domain. These are our independent variable, or this is our independent variable. And that's independent, indi, for independent variable. In fact, I can probably write it on the other side just as well. This is our independent variable, or our domain. These are the values we're going to put in for t here. Done by hand, we'd write this as 0.5 times 1 plus 1. We can either use a calculator or the order of operations. 0.5 times 1 is 0.5 or 1/2, and 1/2 plus 1 is 1.5. Now notice when I go to substitute the 2 in, oh, this is our range, or our dependent variable. Get a little sidetracked there, or our dependent variable. Independent and dependent are terms that my class is very used to me using. We need to substitute this 2 in, so we take 0.5 and we multiply it by 2, what we're substituting in for t, plus 1. 0.5 times 2 is 1, and 1 plus 1 is 2. So when we put in 2, we got out 2. Now watch what happens when we put in 3. Our independent variable is 3. What happens when I put 3 in? Well, first off, the 2 changes to a 3, or the t changes to a 3. We have 0.5 times 3. Now 0.5 times 3 is 1.5. And 1.5 plus 2 is 2.5. So when I put in 3, I got out 2.5. Our last input value is 4, or our last domain value is 4. 0.5 times 4 is 2. 2 plus 1 is 3. So here we have our domain, 1, 2, 3, and 4, and this is our range, 1.5, 2, 2.5, and 3. So this is our answer because it asked us to make a table. It says evaluate the function rule f of g is equal to negative 2g plus 4 to find the range for the domain negative 1, 3, and 5. Well, this is another way of doing what we just did in example 3, but we're not asked to make a table. When it tells us that the domain is negative 1, 3, and 5, this is telling us what we need to substitute in for g. In our function or our equation, f of g is equal to negative 2g plus 4. We have 3 problems to solve here. We have to put negative 1 in for g, and I'll do that right here. And you know I'm putting negative 1 in for g because I replaced the g here with negative 1. And then negative 2 times, I replace g with negative 1, or I use the substitution property. And then I add 4. Here, you can either go for your calculator or you can do some math. Negative 2 times 1 is 2, and 2 plus 4 is 6. So when I put in negative 1, I get out 6. We need to do that again, but we need to move to this number 3. We need to say f of 3 is equal to negative 2 times 3 plus 4. Now, you might be asking yourself, well, where did the negative 1 go? Where did the g go? What I did is I took this and I just substituted it in, the 3 in for g each time. I just didn't rewrite what I have here in red. So in essence, I'm doing the same problem 3 times. I'm just using 3 different numbers. And I'm not copying what's in the red every time, just to save myself a little bit of time. So now I do my math. Negative 2 times 3 is negative 6, and negative 6 plus 4 is negative 2. Finally, I use this equation again, or this function again. And I substitute in 5. So I have f of 5 is equal to negative 2 times 5 plus 4. It should be a negative 2 right there. Then I do the math. Negative 2 times 5 is negative 10. Negative 10 plus 4 is negative 6. So my range in this case, very formally written, for perfect 100% credit would be negative 6, negative 2, and 6. Given this domain, here's my range. This has been Mr. Pilarski on relations and functions. Remember, relations and functions have to do with domains and ranges, inputs and outputs, x values, y values, independent variables, dependent variables. Who are you going to depend on to help you with your math? Thanks for watching. Bye-bye.